we've been asked, how close is the approximation sine of x is approximately x when the x's are between minus 0.001 and 0.001, when the absolute value is less than 1/1000th. So I like to think about that as this interval. Well, this idea that sine's approximately the same thing as x when x is near 0 keeps coming up. The first time we met that was back in Calc 1 with this limit, which you might have established using the squeeze theorem and some areas. You might have looked at the unit circle. Later on, you could use L'Hopital's rule. In Calc 2, we can actually use a Taylor series to show that this limit is 1. But the idea is that the closer theta gets to 0, the closer sine and theta get to being the same thing, which is where this is coming from. Well, now we have the tools to address, well, how close is it? How good of an approximation is it? All right, well, I recognize x there as the linearization of sine, but I also recognize it as the first Taylor polynomial, the first order Taylor polynomial for sine. So if I think about sine being its Taylor series, I recognize that I'm using this first term, right, t sub 1, which is also the linearization, right, the standard linear approximation of our function, to approximate sine, which means all of this becomes my remainder. But I also notice that this is an alternating series. And we know that the error in an alternating series is less than the absolute value of our first unused term, which for us means our error, that remainder term, is going to be bounded by the absolute value of x cubed over 3 factorial. Well, if we use the worst case for x, make x as large as it can be, then we will get a number that's even larger than that. So we'll know that our error has to be smaller than this number. All right, so let's do a little calculation here. 0.001 to the third divided by 3 factorial, which is 6. All right, and that's 1.6 repeating times 10 to the minus 10th, which tells me our error is less than 0.000000000. 1, 2, 3, 4, 5, 6, 7, 8. One more 0, 1, 6 repeating forever. So let's see, how close? Well, this close. Actually, better than that. That's kind of like an upper, well, it's not like an upper bound. It is an upper bound. Please pretend I didn't say like just then. But our error is smaller than that. We are really, really close, which tells me for small values of x, x's that are less than 1/1000th away from the origin, this approximation is actually very good. So that's it for now.